Hello, I'm Albert Ruther, and I am a computer system architect and computational engineer at the MIT Lincoln Laboratory Supercomputing Center and the MIT SuperCloud team. In this section, we are going to compare the storage systems on laptops to those of a supercomputer. As we discussed in the introduction, the components that store your code, applications, and data in preparation for being executed and analyzed is the storage subsystem. The green arrows point to them in both our laptop on the left and our server picture here on the right. Let's take a closer look at what HPC storage arrays look like on the next slide. Here are a few more pictures of a high-performance parallel storage array. They are comprised of one or more array controllers which handle the file system metadata and orchestrate file system transactions. And then there are the data storage servers. There are usually multiple array controllers for greater parallel processing and redundancy. And there are usually many data storage servers to expand both the storage capacity as well as scale up the parallelism with which data access can be executed. On the right, we see what the inside of a data storage server looks like. There are usually many tens of disk drives all packed into the server, along with a storage control computer that manages how data is striped across the disk drives. These drives are usually spinning magnetic platter drives, though some arrays are being built with solid-state drives for faster access times. Let's look at both of these technologies next. It is worthwhile to first discuss the inner workings of storage devices themselves. Magnetic platter disk drives have been around for several decades. These disk drives record data onto one or more enclosed rotating magnetic platters using a read-write head at the end of an actuator arm. To write or read data, the actuator arm must move the head over the intended track and time its reading or writing activities precisely to when the correct track sector is under the head. It is the actuator arm movement which usually incurs the most latency of read and write activities, and modern disk drives have special memory buffers to help overcome many of these latencies. Another interesting aspect of disk drives is that they maintain a file allocation table which records on which platter, track, and sector each data item is located. The file allocation table is stored in the inner tracks, while the data is stored on the rest of the tracks. Let's continue this discussion by comparing the magnetic disk drive on the left with the solid-state drive on the right. In contrast to the rotating magnetic platters of the disk drive, a solid-state drive reads and writes data into transistor circuits within one or more chips. Those chips are labeled NAND flash on the diagram on the right, but NAND flash is just one of several technologies used to make such storage chips. Because data is written and read from transistor circuits, solid-state drives have much lower data access latencies and much higher data rates. But the transistor circuits have a finite number of read-write cycles before they become unreliable in storing information. So the controller manages where data is written to get the best reliability and performance for the device. Now that we've talked about the storage devices themselves, let's move on to an overview of parallel file systems. So what makes parallel file systems perform so well? Well, parallel file systems like the Lustre parallel file system that we use on the SuperCloud are parallel computing systems in their own right. They are high-performance computing systems that are specifically designed to store and move data to and from where the data is needed. These file systems employ an object-based methodology, which means that each file is stored in the data servers and the location of the data objects is managed by metadata servers. In that regard, parallel file systems are comprised of many hardware and software components. Let's look at this further in the architecture diagram on the right. Client software is installed on each compute node, and this client software takes file read and write requests and communicates with the servers to satisfy the requests. The metadata servers depicted at the top of the diagram maintain the state of all of the files and folders within the file system. And finally, the data servers or object storage servers store all of the data of the files. To deliver top performance, the data of each file is striped over multiple data servers and across many disks within the data servers. Given that the architecture that we just discussed, let us follow the activities involved in reading a file in the Lustre parallel file system, like the one installed on SuperCloud. At number 1, a program running on a compute node requests access to a file. Let's say that it wants to read the contents of the file into memory. The Lustre client on the compute node receives the request from the program, and it gets to work. At number 2, the Lustre client first makes a request to the Lustre metadata server for access to reading the data in the requested file. The metadata server responds with a list of the data servers to which the Lustre client must connect to receive the data of the file. Then in number 3, the Lustre client contacts each of the data servers to request the data of the file. And in number 4, the data is transmitted back to the Lustre client from each of the participating data servers. These transfers are accomplished in parallel, and the complete file is reconstructed in the client on the compute node. This example was for reading a file of data, and writing occurs in much the same manner with interactions with both the metadata servers and data servers.